Okay, so today finally we are getting into like the real content or topical physics that's going to be tested on the exam and also gone over in your regular school. So we're going to deal with motion first, and motion is the study of how things move, right? In the English language, you want to know that. And in particular, there are three things that proper terms that we use in physics that's going to be crucial: displacement, velocity, and acceleration. And we're going to dive deeper into what each of them mean and how they're related to each other as well. Also, there is a fourth dimension that we also need to pay attention to, which is time. So people often talk about kinematics or the study of motion as a study of displacement, velocity, acceleration, and time. Okay, all right, so before we start, let's take a quick guess. Two small heavy balls have the same diameter, but one weighs twice as much as the other. The balls are dropped from a second-story balcony at the exact same time. The time to reach the ground below will be A, twice as long for the lighter ball, B, longer for the lighter ball, but not as twice, C, twice as long for the heavier ball, and then D, longer for the heavier ball, but not twice as long, and then E, nearly the same for both balls. Okay, so take a guess. Okay, cool. Quite a few different choices you guys made, but let's move on. So why do we study motion, and how come motion is such a like introductory course for the physics? Because it kind of goes into everything. One very important thing to know for physics is that it's very much so interrelated. The topic we're doing right now, motion or kinematics, is going to carry over to the next unit. When we study force, you need to have a solid foundation of motion to understand force. And then the chapter after that, momentum, you need a solid foundation of motion to understand what momentum is. So physics is a subject that's everything is kind of interconnected. It's not like even math, there's a disconnect, like what you study in algebra may not apply to what's happening in geometry, but physics is very much so connected. So that's why we definitely need to, from the very beginning, from day one, when your school year starts, pay attention. Okay, there's no way you can skip kinematics and then be okay in the later course. So motion, of course, when it comes to racing, when it comes to things that deal with high speed, when you're designing a train, designing an airplane, of course, you need to pay attention to the acceleration, to the motion, and all that to avoid accidents, to avoid fatalities in a way. Also, perhaps the study of motion of like blood cells in your veins to help doctors and physicians understand how our body functions, why blood flow behave the way they do, and help us defeat some diseases potentially. And also tectonic plate movement, literally, is what causes earthquake and natural disasters. So perhaps learning why they move in a certain way, or in what ways can we potentially predict or anticipate motion that could help us mitigate some of the issues. Now, we're not going to start with anything nearly as complicated as that. We're going to start with one-dimensional motion. So what does one-dimensional mean? It means that you are moving in one positive or negative direction. So if I draw a number line, I am strictly moving along the number line. I can move right, I can move left, but I cannot jump out of the line, right? Because that's no longer one-dimensional, right? So one-dimensional motion, always in one direction, either forward or backward, left or right, no sideways, no ups or downs, just that, okay? So from the driver's perspective, you're going forward or backward. From the observer, it's like left or right. Or if you draw your axis like this way, then you know it could be also up and down. But yeah, it does not allow sideways motion. Okay? So that's what we're going to start with. Now, it has to be a straight line by definition, because anytime you have a curve, you are necessarily, as we decided last time, we can decompose any sideways vectors into component form, right? So by default, if it's a sideways thing, you will have a y component, a x component, right? So anytime you move along a curve, you are no longer doing one-dimensional motion. And also, what we are dealing with right now is just how to describe motion. How is something moving rather than what is something moving? That will be the next chapter on forces or dynamics. But right now in kinematics, we're just looking at motion itself, how to describe that. And we're treating all moving objects like a particle or a single dot, right? We're not considering like extended shape. So for example, if we're studying a car, I just treat the car as a single point in a graph. I wouldn't consider like how the wheels are rotating or the tires maybe moving differently than the trunk of the car or something like that. That's a little bit too complicated for now, but we're just going to treat any moving thing as one single point in space. That's all. Okay, with all those kind of necessary simplification of our world, let's talk about how do we describe these things. Hold on. I think one thing I want to add that I can't believe I didn't put it in is that this chapter or this unit is called kinematics. And kinematics is simply defined as the study of motion. Okay, kinematics, the study of motion. That's it. All right. Now, let's talk about these common English language words, right? You've all heard them, you've seen them a lot, but how do we define them as physicists? So position, displacement, and distance, they are very similar. So first of all, position is literally the location of an object relative to some reference point, right? So for example, if I have Tom here, and I have Jack here, and I have Rachel here, and I have, let's say, Nancy here. So if I were to describe the position of Rachel from Jack's perspective, not from Jack's perspective, from the viewer, from your perspective, but treating Jack as the reference point, we can say Rachel is one spot to the right of Jack, right? So we're using Jack as a reference point. Or you can say Rachel is two spots to the right of Tom, right? Both will be fitting and correct description of Rachel's position. However, if you just look at the number, one of them is one of them is two, they're definitely not the same, right? So therefore, when we're describing a position, we definitely need to make sure we have a common understanding of what the reference point is. And the very important like application of that is in, let's say, astronomy, right? If we're describing the position of Earth in our solar system, are we treating our sun as the reference point? Sorry. How far away is Earth from the sun? And if we're talking about the location of Mars, are we talking about the Mars as opposed to the sun, or we're talking about Mars as opposed to the Earth? All right, so that's going to be very different descriptions of how these planetary motions are working. Okay, all right, so that's that. And normally for a one-dimensional thing, we're just going to have like a number line or position line, and we mark our reference point as the position 0. I think that's very obvious. We call that the origin. We call that the 0 position. That's the reference point. So this thing here, if I label it 3, that will be 3 units to the right, or plus 3. And then if I have like a -1 here, then that position is -1 to the left, right? So the signs will tell you it's in the positive or negative direction, and the number will tell you how far away you are from the reference point or the origin. Okay, so all that is very straightforward. I don't think there's any confusion with that. So key thing to know, positions can be either positive or negative, indicating their relative position to what direction it is compared to the origin. Now, displacement. A displacement is defined as a change from position 1 to position 2. So it is always a difference. You can never have like an absolute displacement. You're always having displacement from one point to the next. And therefore, displacement defined as delta x is x2 minus x1. Now, let's say if I moved from point, our number line, if I move from point -1 to point 4, What is my displacement? That's a very easy question. Aiden, do you want to give it a try?
From 0 to 4.
From -1 to 4. If I start from -1, I move to 4, what is my displacement?
Plus 5.
5. Yeah, very simple, because you're just going to do 4 minus 1, you get a 5. Okay, Eddie, why don't you help me with the next one? What if I move instead from 4 to -1? What is my displacement? Very good. However, this is the next thing I want to talk about is because what we want here, also, we are allowing displacement to take negative values. In this case, I will say the motion from 4 to -1, the displacement is -5 because I'm moving in the negative direction. Okay, all right, so that's that. And notice also that this displacement definition doesn't care the pathway you take, right? Doesn't take into consideration the pathway you take. All it cares about is where you ended up with, where you started with. Always is endpoint minus beginning point. That's the displacement. And the displacement, again, we are having magnitude. How far exactly did you move? Or the absolute value of your displacement is called the magnitude. How big is that number? And then we also allow a sign to indicate whether you're moving forward or backward. Okay. Displacement here is an example of a vector quantity, which is a quantity that has both the direction and the magnitude. We did that already. So this graph, oftentimes we, oh, where did I put this? Okay, all right. So this graph shows with respect to time t, so this is t equal to 1 second, t equal to 2 seconds, what is the position? This is the position versus time graph. What is the position of my, if they say armadillo? So my armadillo is staying at the same position, right? It's always at x equals to -2 meters from the audience. So if I draw on a number line, my armadillo is staying right here, not moving, right? So that's what this graph means. But what if I say, okay, I am riding a bicycle to the school from home, and I'm going to treat my home as my 0 point. And as t goes on, my position is doing that, right? Maybe 1 minute later, I am 50 meters away. That's really fast. No, never mind. 1 minute. Yeah, 1 minute is fine. 1 minute later, I'm like, let's say 100 meters away. And then 2 minutes later, I am 200 meters away. So this is my position, right? So let's say these are my 2 points. Okay. Then someone may ask the question, this is my x, being measured in meters. This is t measured in seconds. Somebody may ask the question, okay, so what is the displacement between 0 and 2 seconds? What is the displacement between 0 and 2 seconds? Well, the answer is I've moved from 0 meter to 200 meter, right? So therefore, my displacement is 200 meter in 2 seconds. Okay. Now, let me ask another question. What is the displacement between 1 second and 2 seconds? And Jared, can you help me with that? What is the displacement between 1 second to 2 seconds?
100 meters.
100. Yes, exactly. Good job. Because moving from 100 to 200, I've moved 100 meters right here, right? So that's that. Good job. That's that. So that's how you would get displacement on the position time graph. You literally calculate the y difference between any 2 points. Yeah. Given even later on, if you're given more complex graphs, like for example, this one. If I'm interested in finding out the difference between this point, displacement between this point and this point, all you needed to do is look at the y value, right? What is the difference between y value? That's the displacement. Okay. All right. Cool. Yeah. Now, the total displacement then is kind of kind of like not really something that's no, I'll show the example first. So what if, like, let's say step one, I have a displacement of +5 and I started with -5. Where do I end up with after my first step? I will get to 0, right? So step one, I go a little bit better. Okay, that's my step one. Okay, and what about if in step two, I say, okay, I have a further displacement of -3. Where would I go? I would go back here. Okay, -3. And then in the fourth step, in the third step, maybe I say, okay, what if I have another motion with a displacement of +10? What would you get? You would go from here all the way to 7, right? How do I know that? Because -3 plus 10 is 7. Okay, so that's that. And then if I ask the question, what is my total displacement? How would you do that? Well, one way you can do, you simply add up all the steps and you're going to get 12, right? Plus 12. Is that correct? Yes, because again, by definition, the total displacement should be just your xf minus your xi. F for final, I for initial. Where's my ending point? 7. Where's my beginning point? -5. So if you do it this way, they give you the same result. So for total displacement, you can simply add up all the steps that you've taken, or you can just ignore everything that happened in the middle, just find out where you ended up at the very last moment, and then what's your beginning moment, subtract them, that's total displacement. Now, all that will sound very intuitive, and why are we even talking about that? All right, it seems so easy, you've done that in elementary school, seems like. However, the reason why it went through the details is because now we're going to contrast that with distance traveled. So distance traveled is a different quantity from displacement. Okay, they are very different things, and distance will not be negative. Distance is an absolute value term that only cares about the ground that you covered and not about direction. So distance is a scalar, not vector. It will not have a direction on distance. So let's do the same thing. I'm going to copy what I did there. Let's say I have these 3 steps, right? Where's my select picture? Just along that and then leave it there. Okay. All right. So again, these are my 3 steps. So the distance traveled then would be from -5 to 0, sorry, to 0. So how far? If you're thinking about you're driving a car, if you're looking at the mileage meter, I know you guys don't drive, but you probably know a little bit about it. Like if because the car tracks how many miles you've driven, right? So let's say I drove 5 miles this way, and then I decided, you know what, I'm gonna go back home. I forgot my laptop at home or something, and I started to go back for 3 miles. And then I realized that, you know, the backpack is actually in the trunk, so I don't need to go back. And I went forward to try to get to my original destination, right? Something like that. And then the distance traveled then is really caring about how much ground did I actually cover? How much gas have I actually burned? So therefore, the distance travel would be, I traveled 5 here, I traveled 3 here. Again, because distance doesn't care about direction, it's just 3. So I'm taking the absolute value of all these things and then adding them up. So in other words, I'm doing 5, 3, and 10. So the distance traveled is 18 instead of just 12. I think that was the displacement, right? So even though I'm doing exactly the same motion, the total displacement is 12, and the distance traveled is 18. Okay. And how do you physically understand that? Like, so the total displacement in a way is like just the difference between your positions. Let's say I've gone, let's say this is my home and this is my supermarket I want to go to. right? The displacement is literally how far off are these 2 points. What is the raw kind of direct line difference you're going to get? So for example, I know we're doing one-dimensional, but let's say we're doing two-dimensional traveling. The displacement or the thing between 2 points are simply how long this straight line is from A to B. But if you travel, because we don't fly a helicopter, we would have to drive on the road. If your travel does more like something like that, the exact length of this curve that I draw will be the total distance traveled. But the displacement is just that. Yeah, okay. Hopefully that makes sense to you. Are we okay? Give me a nod or a thumbs up to let me know. Okay, all right, cool. All right, so checkpoint. So I'm gonna put in some questions and then you guys help me solve, okay? All right, let's see here. Okay, 6 questions. Please do try to work them out and let me know answers. You can type to me in chat. Yeah, that's right. 6 answers should be really quick. Yeah.
Wait, Mr. Ru, what does it mean when you say what is a position? Like what is like where you're at right now, or like?
Yeah, pretty much. Once I finish
Okay.
the motion, where am I at? Where
Okay.
am I at? By the way, you can call me Chris. Don't be so formal. I'm much more used to just people calling me Chris.
Okay, sounds good.
Yeah. Okay, good. All right, a few of you have given me the answer. All right, great. So I'm going to start slowly writing them down. Position of A is simply at -1. If you said something about like 1 to the left of the origin, that's fine. But I think we can just agree that's at -1. That's fine. If one travels from A to B, that's a position change of 3. So +3. If one travels from C to A, what is the displacement? That's -4 because I'm traveling in a negative direction. If one travels from B to C, what is the position? That's just the C. That's where C is at, which is 3. What is the distance traveled if one goes from B to A to C? That is going to be 3 plus 4, 7. And the last question, 3 parts. What is the position if I go from A to B to C and back to A? The position is still at A, that is -1. The displacement is 0 because my final location and my beginning location did not change. So that's -1 minus -1, which gives me 0. And the distance traveled is 8, right? Because I went this way for 4, went back way for 4, so a total of 8. Yeah, oops. Okay, so that's that. Very simple, very straightforward. I think you guys got it. All right, moving on. Now we're gonna go on to the second quantity that we're interested in, which is velocity. And you can notice that aside from velocity, also have some other stuff, but we'll define that later. So velocity and speed is something that we say in daily life a lot as well. Yeah, mostly we say speed. We don't say velocity as much, but in physics world, we actually care about velocity more than speed, and I'll tell the difference between them later. So first of all, we define what is a average velocity. A average velocity is defined as your displacement, the quantity that we just studied, which is the change in the 2 positions divided by the time that it takes to get there. So for example, in this thing that we did, let's say in this step, if one travels from C to A, what is this displacement? It's -4. If I tell you it took 2 seconds to do that, then what is the average velocity? You will say, okay, the displacement of this travel is -4, and the time is spent is 2 seconds. So dividing it, I get -2. But notice we also need to divide the unit because this is measured in, let's say this is measured in meters, and this is in seconds. So you get meters per second as your unit. And your velocity will always have a unit that is some sort of distance or measure of length divided by a measure of time. So commonly you will see things like meters per second is actually the standard SI unit for velocity. You could potentially also say like kilometers an hour, or you can say mph, which is miles per hour, all of which are a measure of speed, that is a distance over a time. Okay. All right, so that's that. So that's the definition of average velocity. And notice how people use a bar on top of v to indicate that this is not just any velocity, this is the average velocity over a period of time. And it's defined by delta x, which is x2 minus x1, delta t, which is t2 minus t1. Normally, we don't usually bother with delta t because it's very rare that we care about like distinctly what T1 is or T2 is. Normally, T1 we assume to be 0. Like we start from 0 seconds and how long it takes. Right? We just calculate with the changing time. But let's say in a very specific scenario, they want you to find out the average speed of a car when it's going like 5 seconds after they start to 10 seconds after it started. You know, it's very specific things like that. You can say, okay, the time duration is then 10 minus 5. But I think it's very intuitive. Time thing is very easy to understand. So. Yeah. All right then. So let's take a look at this problem. Jill sets out from her home to deliver flyers for her yard sale, traveling due east along her street lined with houses. If 0.5 kilometers and 9 minutes later, she runs out of flyers and has to retrace her steps back to her house to get more. This takes an additional 9 minutes. After picking up more flyers, she sets out again on the same path, continuing where she left off, and ends up 1 kilometer from her house. The third leg of her trip takes 15 minutes. At this point, she turns back towards her house, heading west. After 1.75 kilometers in 25 minutes, she stops to rest. Okay, all right. Now, first question. What is Jill's total displacement to the point where she stops to rest? So she stops to rest at the very end, right? So what is the total displacement in this long-winded traveling thing? Yep. Okay. I think Aiden got it right. Good job. So I kind of lied. Sorry. I thought this. I thought. Never mind. Okay. All right. So essentially, the final displacement is negative 0.75 km if we have defined the eastward direction to be positive, right? If we define it the west to be positive, then we have a different answer, it'll be positive. But let's assume going east is positive, and then going west is negative. Then it's going to be negative 0.75 kilometers. Why? How do we know that? Well, the key thing is that here it says ends up 1.0 kilometers from her house. That's still going east, right? And then the third leg of a trip is going backwards towards her house, and then goes 1.75 kilometers. So it's 1 plus 1 and then minus 1.75, because this is going backwards. So we're going to get 0.75 negative 0.75. So we're 0.75 to the west. That's the final position. Okay. I would just say like 0.75 to the west. Okay. What is the magnitude of the final displacement? So I guess we can say this is negative 0.75 here. And of course, I should include my unit, which is km. The magnitude is the absolute value, so it's 0.75 kilometers. This is the question one asks. What is average speed during her entire trip? How do we do that? Remember, our average velocity is defined as the total displacement divided by the total time. So the total displacement is negative 0.75, and the total time, well, it took a while. So it's first 9 minutes, another 9 minutes, then another 15 minutes, then another 20 minutes. So altogether, this is negative 0.75 divided by 53, right? And we're going to get an answer. Let me use the calculator. Negative 0.75 divided by 53, I get negative 0.014. It would continue with 1.5. However, because I noticed this is a 2 significant figure thing, this is a 2 significant figure thing, I'm going to only keep 2 significant figures, which means I'm going to cut it off here. So rounding 1 rounds down, so negative 0.014 kilometers per minute, right? That's the unit because we're dividing. That's 53 minutes down below. So that's that. That's going to be the average velocity for this entire trip. Now, what is the total distance traveled? What would you do? Well, I traveled a 0.5 first, another 0.5, even though it's backwards, but I don't care. Distance just cares about my raw magnitude. And then I traveled 1 kilometers, and then I traveled another 1.75 kilometers. So altogether, that's going to be 3.75 kilometers. Okay, and then we need to make a graph of the position of versus time. So that part, let me do on the left. So starting from 0 minutes, let's say in 9 minutes later, I went up to 0.5, right? So let's say this is 1, this is 2, this is 3, and then, oh, sorry, should label this 0.5, 1, 1.5, and then 2. And I have negative 0.5, negative 1, and that's my coordinate, right? And then what happened 9 minutes later, I get back home. So this is at 18. And then later on, I really shouldn't say this in the meter. This is t measured in minutes, and this is gonna be x measured in kilometers. Okay, so 18 minutes later, I get home, and then I traveled for 15 minutes, so at 33, I will get to where? I will get to 1 kilometers away, right? So about here, and after that, in another 25 minutes, so at 58, so that's quite a far away here. So maybe somewhere here. Let's say that's 58. Again, this is not drawn to scale, but I think you get the point. And I'm down to negative 0.75, so somewhere between negative 0.5 and negative 1, and then goes a straight line there. So that will be the graph, the position versus time graph. Yeah. All right, cool. So that's that. Let's try another one. You drive a beat-up pickup truck along a straight road for 8.4 kilometers at 7 kilometers an hour, at which point the truck turns, runs out of gas, and stops. Over the next 30 minutes, you walk another 2 kilometers further along the road to a gas station. What is your overall displacement from the beginning of the drive to your arrival at the station? That should be a fairly easy question, so let me know. What do you guys think? What is the total displacement? Yep, that is correct. 10.4, right? The total displacement is 10.4. I was driving for 8.4 kilometers. After I ran out of gas, I walked another 2 kilometers. So altogether, it's just 8.4 plus 2, 10.4. I don't know why there's no B part to it. So the B part is, I'm now going to ask the question, what is the average velocity of the person's walking speed? And try to convert that to kilometers per hour. Let me type that up 1 second. What is the average velocity of this man walking? And use kilometers an hour for that. Okay, good. I'm getting correct answers in the chat now. Good job. Yes, indeed, it's going to be 4 kilometers an hour. How do we do that? Well, since I'm only concerned about walking, so what is the total distance he walked? He walked 2 kilometers, right? So 2 km is the displacement. How long did it take? 30 minutes. But since I want hour, 30 minutes is essentially half an hour, so 0.5 hours, right? And therefore, 2 divided by 0.5, I will get 4 kilometers per hour. Yep. If you didn't do that, if you want to do 30 minutes, then you will get, let's say, 2 over 30. So 1 over 15, I guess. 1 over 15 kilometers per hour. Then you will need to convert this to, I want to cancel the hours. So for 1 hour top, 60 minutes on the bottom. And this becomes wait, no, sorry. This is 1 over 15 kilometers per minute. I want to cancel out the minute. That's how I get the hour. So I put 60 minutes on top, 1 hour on the bottom. Minute will cancel. 60 divided by 15 is 4 kilometers an hour. Right, so it's the same thing. Whether you did the conversion later or whether you did the conversion at the beginning. Anyways, so that's that. Now, my third question. What is the average velocity of the entire trip? This one is a little bit tricky and may take some thinking to it. Okay, so let me just go through this because I think it's a little bit tough. So one thing that people may attempt to do when they see the words average velocity, and we know there's 2 velocities I'm given, 70, and then the other one is 4 that we calculated. So some people might attempt to say, okay, since one of them is 70, one of them is 4, how do I get average? Oh, I'm just going to add them up and divide by 2, right? That's normally how we do average, and we'll get an average velocity of 74 divided by 2, so 37. And that will be incorrect. You cannot do that. That is not the average velocity. The reason for that is you are not taking the average of just these 2 velocity numbers, because I walked with this speed for half an hour, but I have no idea how long it took me to drive. Maybe you only drive for 1 minute. Maybe you drove for 7 hours. I don't know, right? So it's not equally timed spent. If I have equal time on both, then I can actually do that. But in this case, I don't know. It probably won't be the case. So therefore, the way to solve average velocity is to go back to the definition of what the average velocity is, which is the displacement, total displacement over total change of time. Do we know the total displacement? Yes, we know. We solved it in part A, 10.4 kilometers. But do we know what the total time is? I don't. Well, I know the second half of the journey is 0.5 hours, but do I know the first one? I do not. But can I solve it? Sure, because I know for the first part of the journey, it's 8.4 kilometers at this speed. So therefore, what is velocity again? Velocity, so in a way, this is the velocity of the first part, and that should be the delta x of the first part divided the time spent on the first part, right? So how do I solve for time? Well, time will be delta x1 divided by v1 bar. How do you make sense of that? All I did is I swap places. It's like 3 equals to 6 divided by 3, then 3 is 6 divided by 2, right? You can swap these things, right? Part of the from division. So that's that. So therefore, the time I spent on the first part of the journey is simply going to be 8.4 kilometer divided by 70 kilometers an hour. And if you do the division, this is 0.12 hour, right? And that's that. And again, don't overthink this, because if I just told you I've driven 8.4 kilometers at a speed of 70 kilometers an hour, how long did it drive? And you would tell me you just divided by, right? Because this is you've done this in elementary school. What's the relationship between speed, time, and distance? Distance divided by speed is your time. Distance divided by time is your speed, right? And it's just simple as that. Okay, so once I have that, now I can plug it in. So 0.12 here. And now calculating the total with the help of a calculator, because I'm lazy. And most likely you're going to be allowed calculator for much of the physics course, since this is not really a math class. Okay, so 10 point, and you're allowed to calculate on the AP exam, 0.62. And I'm going to get 16.774. How many digits do I want? The least amount of the figure here, I think, is 0.12. And 0.62, that's two decimals. I mean, two significant figures. And you might wonder, why is it not just one sig fig? Isn't this number just one sig fig here? Well, this number I got by converting 30 minutes to 0.5 hours, right? So 30 minutes, technically, I suppose I have a two significant figures. So really, if I'm being strict with myself, I should probably say this is 0.50 hours. So that's why I still have two significant figures here. And then, yeah, there we go. We should round it to two significant figures. So 17, right? 16.7, 7 something. That rounds up to 17. Not 71, 17. Right, so that's my final answer. The average velocity of the entire trip, including the driving part and the walking part, is 17 kilometers an hour. And guess what? That's much lower than I would say the dumb way of finding the average, which is the wrong way, which is the 70 plus 4 divided by 2, right? That will give me 37. That's way different, right? 17 is so much lower than 37. But yeah, so that's all. This is the average speed. Okay. All right, cool. With that, let's talk about instantaneous and average speed. So in the physics course, you are going to be caring about both, if not instantaneous more than the average. By the understanding of common English language, you probably see the difference between them. Instantaneous is at that moment. Let's say right now it is June 25th, 5 o'clock, 24 minutes, 33 seconds. At this exact moment, what is my speed, right? While the average speed is something over a pretty lengthy time period. So let's see here. Can I get the ticket? Officer, my drive from LA to Cupertino was 350 miles and it took me 7 hours. So my speed was just 50 miles an hour. Nothing wrong with that, right? I divided my total distance by my time, so I get the speed. I didn't break the speed limit of 70 miles per hour. Why am I getting a speed ticket? Well, because this number is what? An average velocity, right? This just calculates overall, including the time I might have stopped for bathroom or lunch, that I'm not moving, and including the time that I'm probably driving really fast. And the overall average is 50 miles per hour. Or at one particular instant, I could be driving 70, I could be driving 80, I could be driving 90, for all I know, right? So therefore, this is not a good argument. Don't try that on the police officers because they know that, right? Yeah, because the instantaneous velocity is different from a average velocity. And if we think about this, looking back at the graph we made earlier, if I were to find the average velocity on a graph, how would I do that? Let's say I'm interested in the average velocity of this entire trip when I went from 0 to negative 0.575. So my total displacement is negative 0.75, but the time I spent is 58 minutes, right? So if I divide negative 0.75 by 58, I think I got a number on that, right? That's, yeah, negative 0.014. With the kilometers per minute, right? But how does that show up on the graph? That is the decline slope. Remember the wording. Average velocity, I should probably type it. That's all. Average, I should prefix it, on a position versus time graph, the average velocity is the slope of the secant line, and the secant line goes between starting and end. Okay. All right, so that's that. So the slope here, if I, yeah, you guys know what the slope is, right? And you guys know what the secant line is, I assume. Yeah, we're okay. All right, okay. Then I may ask the question, what is my speed here at this, let's say the green point over here? What's the speed there? That's not negative 0.014. I'm clearly going forward. In fact, I'm going forward from 18 minutes to 33 minutes. I spent 15 minutes and I traveled a positive 1 kilometer. So my speed is actually 1 kilometer, or my velocity, divided by 15 minutes, right? And let me do that. That is 1 divided by 15, roughly 0.0, 0.067 kilometers per minute. Right. And how do I know that? Because I'm going up. So the slope going up is that. Okay. And guess what? The slope over here will be some negative number. The slope over here will be a positive number. It's literally the slope of the line. And to understand that, and let's use the formal language. You can say the same thing on a position versus time graph. The instantaneous, I'm trying to spell it right. Instantaneous velocity is the, I don't need the comma, is the slope of the tangent line of the graph. Okay, and when we have straight lines, if the graph itself is a straight line, then the tangent line is just a straight line. That's fine. However, if you have graphs such as like these, like curvatures, a tangent line is something that does this. Like it's just barely touches it and skims through. Like it may cut across graph like further away, but it doesn't matter. Like this, like a tangent line will be here, right? And the slope of these kind of lines that just barely touches it at the point of my interest, and this one will have like a zero slope here, are called tangent lines. These are called tangent lines. So the position with position with time graph, the instantaneous velocity is you pick your point that you need, and then you draw a tangent line and the slope on that. Okay, you're almost never going to be asked to do this by hand in what's it called, the AP exam. However, I'm pretty sure you're probably going to do like an experiment in your AP physics side, and you're going to try to get a slope by graphing it and whatnot. So that's that. Okay, cool. So that is that. Now we're going to talk about the graphs. You know what? Let's stop here and let's take a break. We've been going for an hour. Let's take a break for 10 minutes. Come back at 5:40 and we'll continue. Okay. All right. Take a break. Okay, let's go ahead and continue. All right, so yeah, once you're back, please turn on the camera again so I know you're back. But yeah, let's go ahead and jump back in. So we have these graphs, position versus velocity graphs. And so first we have a position graph. So these two are actually a pair. So what do I mean by that? If I look at the position graph here, what's going on? I am moving from 0 position to 3 in about, I don't know, 0.25 seconds, right? So therefore my speed here, or my velocity here of this leg of the journey is going to be 3 divided by 0.25, which is about 12. And that is my velocity. So if I plot a velocity versus time graph, I'm simply traveling at a constant velocity of 12 up to that point, right? Notice how they're matching here. the slope of the position versus time graph is the value of the velocity versus time graph. Now, at this point, I suddenly shift gear and I started going backwards, right? And the velocity of the second part of my journey is going downwards by 3, right? Going from here to here, that's -3 divided by the time it took is 0.25. So it's exactly -12, same calculation. So my velocity all of a sudden jumped to -12. This is actually like purely, let's say, uh, theoretical, because it will not happen like that. Normally, you would have some sort of, it's not going to be instant. You're going to like decrease your speed and then go down and then start to go. It's not going to be perfectly a straight line as being illustrated here, but you can kind of imagine this is like you throw a ball at a wall and it just bounces back, right, with the same velocity. That's kind of what's going on. The ball is going towards the wall, boom, and then hit the wall and then bounces back. It's almost instantly it changes from a positive velocity to a negative velocity. But in reality, there's like a split second that's going to be like a very, very negative slope. That, yeah. Anyways, so that's that. Now, the velocity graph is the one that we're going to see a lot, and the one that's really helping physicists because I can see when I'm traveling forward, when I'm traveling backward. When I have a positive velocity, when the graph is above the 0 axis, I'm traveling forward, right? A positive velocity means I'm going forward. A negative velocity is going backward. As opposed to a speed graph, in this case, the speed is going to be 12 the entire time. Whether I'm going forward or backward is going to be 12. And it's not very like, it doesn't tell me much information. So, but this is actually what happens in your car, because your car clocks your speed. It doesn't really clock your velocity. So whether you're driving west for 60 miles per hour or you're driving east 60 miles per hour to the car, to the dashboard on the car, it just says you're driving 60 miles per hour, right? So that's that. Yeah. Okay, let's take a look at this question. A commuter train travels from Baltimore to Washington, D.C. and back in 1 hour and 45 minutes. The distance between the two stations is approximately 40 miles. What is the average velocity of the train and what is the average speed of the train? Let's give that a try. Hey, I see some answers in chat. Good. All right, let's start with this. So A, Riley, why don't you explain to me how do you get that answer?
So you have to find the displacement, but the displacement is just 0 because you're traveling there and back. And then, yeah, so 0 over the time, like 1 hour and 45 minutes, so it's just going to be 0.
Yes, exactly. Because velocity, we do displacement over time. Displacement is 0 because we're going from Baltimore to Washington and then back, right? So therefore, it's just big O 0. That's right. And then for part B, we actually need to do some calculation because we did go there for 40 miles. And then we also come back for 40 miles. 40 miles. And then on the bottom, maybe 1 hour and 45 minutes is 1 3/4, right? So I can say this is maybe 7 over 3 hours, right? So do that. That's 80 divided by 7 over 3, which is the same thing as 240 divided by 7 miles per hour, right? But now I need to convert miles per hour to meters per second. Again, I want to cancel out the mile. Let's put 1 mile on the bottom. 1 mile is about 1609 meters. And then hour is, we did that the other time. 1 hour is 3,600 seconds, right? So that's that. Put that together, 240 times 1609 divided by 7 times 3600. That's all the numbers. Miles canceled out, hour canceled out, I get meters per second. And check that in the calculator. And we'll get 240 times 1609 divided by 7 times 3600. And I'll get about 15 meters per second. Okay, all right. Yeah, so that's that. And I would say for any physics problems, this is what goes on in my head. Step one, this is very crucial. When I'm dealing with a physical problem, read twice. I always do that. The first time is gonna get a general idea of what the question is talking about. And then the second time, I'm really like annotating and highlighting, kind of like, okay, what's the key information that's there? And then you kind of do this with the second step as well, is think what concept apply, right? In this case, as I'm reading it, I know, okay, this is a kinematics problem. It is about the velocity and displacement and all that. So I know that's kind of the thing they're testing. It's not about energy. It's not about force. Right now, you guys haven't done so many topics, so it's not a big deal. But later on, when you have so many topics, it's really important to think about like what actually do you think they're testing you on. And the third step is think equations. Once you have the concept, you should be able to link that to several equations that you know of. And then step 4, think about what they gave. Okay, these quantities that they give, what do they represent? What kind of quantity? So for example, in this step 3, I know the equation I'm going to use is delta x over delta t. And I look at these, okay, which was which? Is this t? Is this x? Is this t or is that x or something like that, right? So think about what they give you. 5, think what you want, right? What I want at the end of the day in this question is the average velocity and the average speed, right? And then think about which equations, where in the equation are they, and then fill them in, right? And then step 6 is kind of like filling equations. And sometimes at step 6, when you fill in what they give and what you want to know, you may still have missing information. Then you might need to think like, is there any way I can get that missing information? Sometimes it's a constant that you should have memorized. Sometimes it's an easy calculation that you can get from the other stuff that they give you. Yeah, so that's that. And then finally, step 7, we just solve, right? And that's kind of like the general approach I have for all physics problems, actually. Okay, so actually one last step. Once you solve it, check units. Is your answer in the right unit? If I'm solving for a velocity or speed, in this case, meters per second sounds great. If I'm solving for speed and my unit ended up being seconds, then I know I did it wrong. Somewhere I didn't have the correct dimension. And then the last thing, number 9, like reality check. So for me, a train is moving every second 15 meters. 15 meters is about like, I don't know, like about the length of your house, I think. But every second the train moves forward by the length of a house. I think that's very reasonable. Yeah. But if I got an answer that's like 200 meters per second, and I go that every second is 200 meters. That's like, I don't know, like 200 meters is how many feet? Like 600 feet. Every second the train is moving 600 feet. And I know I got the right unit and everything, but this number can't be right. There's no way for that to be true. So always do like a reality or gut check, or like, does this sound right? Does this sound in the ballpark of number I'm expecting? If it's not, then check your math, check the process. So these really helps when you have extra time on your test. Okay. All right, cool. Yes.
I have a question.
Mhm.
So when we're dividing to get the answer of 15 meters per second, do we not include the decimals because we're dividing by 2 integers?
I wasn't doing this like very strictly, but I assumed we have two significant figures for the numbers that are given. So I'm just keep two significant figures. Yeah.
Okay, thank you.
Okay. All right. Let's move on to the next topic, which is constant acceleration. We are going to largely be dealing with constant acceleration for most of the problems you're going to do with AP Physics 1. And we are going to separate our world into two specific cases. The real world is not going to be one of these. The real world is going to be somewhere in between and not even, sometimes neither of them. But these are the two most common simplifications and occurs common enough for us to have special interest in them. So first one is a constant velocity. This is the world that you are familiar with since elementary school. You've done problems after problems about constant velocity. You're traveling at a fixed speed. You're walking 5 kilometers an hour. You walk for 2 hours. How long do you go? That kind of question, right? So the equations for that is very straightforward. Your delta x is simply your v times delta t, or your v equals to, or average velocity is your instantaneous velocity, and that is delta x over delta t. And your acceleration is 0. And we'll get to what acceleration is later, but knowing that. Then we have a constant acceleration. A constant acceleration means that your v is changing steadily. Okay, your v is changing steadily. So think about like the relationship between delta x and v. Like essentially we're saying with a constant v, the displacement is proportional to the time. The more time you have, the more displacement you have. It's kind of like a linear relationship with t, right? Now, we're going to apply that to v as well. In this case, v is equal to a times delta t. Delta v equals to a times delta t. And we define acceleration as the change in velocity over the change in time. In other words, if velocity is what is that? I'm going to type. If velocity is the rate of change of position, and acceleration is the rate of change of velocity. How fast am I changing my velocity? A strong or large acceleration means that I'm changing my velocity rapidly. A slow acceleration or small acceleration means that I'm slowly changing my velocity. That's that. Okay. How fast I'm changing my velocity. So that's okay. And yeah, so in the constant A world, we are going to have much more complex equations, and these equations you need to commit to your memory. As for constant v, the equations is literally just this guy. That's it. That's the only equation for constant v, and knowing that a equal to 0. Because if my v is constant, that means there's no change in v, hence there's no acceleration, because acceleration is the change, the rate of change of v, right? So let's think about it. So in other words, if my v is changing, right? If my v is changing, then my displacement is no longer just v times delta t, because this v is a changing quantity. It turns out we have 4 major equations we can use for constant acceleration world. First is this one. This is very easy to understand because we define a to be delta v over delta t. Then delta v is simply your v2 minus v1. Here they use v and v0, so let's do that. So this is simply v minus v0. v0 means the initial speed, or the speed you started with, and this is your final speed. So final speed minus initial speed divided by t is your a, then at is v minus v0, then v, your final speed, is your initial speed plus AT, right? So this is very similar to the idea delta V equals to AT, right? A delta T is just I'm writing out what delta V is and then solving for final V. So this is that. This is the velocity equation. Then we have this particular equation. You will learn how to very easily derive this equation when you get to calculus. But now I'm going to show you a relatively complex way of proving that. So, so first of all, let me move this to the left. X minus x naught is just delta x. That's all it is. So don't worry about the x naught too much. It simply means that I'm accounting for the delta x. The delta x is the displacement, right? And we know the displacement would be like, how far have I traveled? So if I have a initial velocity, v0, and for the entire time period, I'm traveling with that initial velocity, right? But on the other hand, I will also have kind of like my ending velocity. What's my end velocity? My end velocity is going to be my v naught plus at, right? That's kind of like my vf. V equals to v naught plus a. That's the first equation that I have. But then that's not the entire time I'm not traveling at that speed. The entire time I'm not traveling at the initial velocity either. So we need to find out kind of like the average between that. And it turns out, since if I'm, let's say if I'm drawing a VT graph, if my V is increasing steadily, it means I have a linear graph of that. And the average velocity is actually just your final velocity and your initial velocity halfway between them. You're finding the midpoint between your two V's. This is your V, this is your V naught, and thus your V bar is simply V plus V naught divided by 2. So delta x is going to be V bar, your average velocity times delta t. In this case, let's just say t. And V bar is V plus V naught over 2 times t. And V here, plugging the first equation that we have, is V naught plus AT plus V naught over 2 times t. Guess what? This is simplifying to 2V naught plus AT divided by 2 times t. And separate them out. V naught, this 2 will cancel, so I guess V naught t plus this, there's nothing to cancel all that, so this becomes 1/2 AT squared, and the left-hand side is delta x. So the change in the displacement is your initial velocity times time plus 1/2 acceleration times the time squared. Okay, so that's that. That's how that comes from. Again, you do not need to know how to derive this. You do not need to know why it is the case, whether the algebra way or the calculus way. Just know you need to definitely 100% memorize this equation by heart, along with these two. This is the average velocity one. That's the one I use. But this one is less useful. I don't think you use this as much. But these three, you use it all the time when we're dealing with motion and we're dealing with kinematics. Okay. So before we apply these, let's see. Do I have an easier problem here? Yeah. Okay. I feel like I'm jumping the gun here. I'm telling you guys things a little bit too fast. So let's step back a little bit. Let's first calculate A. Right? What are some typical calculations of A? Let me give you a question. Let's see here. If a cheetah can accelerate, this is true. Cheetah is the fastest animal on Earth, and the cheetah can accelerate from rest, not moving, to 60 miles per hour in 5 seconds. What is the acceleration in meters per second? Okay. All right. So let's calculate that. If I have 60, I know this is asking acceleration. So the concept of the acceleration, the equation of acceleration is A equals to delta V over delta T, right? 60 miles per hour, that's my V final, right? And I know my V final can go into the delta V. And what is my V initial? They did say I'm going to start from rest. So therefore, my initial velocity is what? V0 equals to 0 meters per second, right? Is that set? And then I'm going to have delta T on the bottom, but do I know delta T? That's that, right? So why don't you guys help me calculate this out, and don't forget to convert units, because we started with mph, but we want meters per second. Let's see if you guys can get the right answer. Okay, I'm getting a couple answers, but it looks like we're having a little bit trouble. So let's see here. On the top, we're gonna have 60 mph minus 0. On the bottom, I have 5 seconds, right? So I'm gonna get essentially 60 over 5, and then the top is essentially miles per hour, and then on the bottom, I still have a second, right? So the unit gets a little bit crazy here, but in other words, I get 12 miles per hour times second, right? But I want oh, sorry, this is my bad. This is the wrong unit. This should be meters per second square. Why is that? Because this one I need to convert in seconds, and miles I need to convert to meters. I'm going to multiply 1609 1609 meters on top, and then 1 miles on bottom, and then again 1 hour on top, 3600 seconds on the bottom. So miles cancels out, hour cancels out. I get meters per second squared. There's going to be 12 times 1609 divided by 3600. And I think we should get something that's like 1609 divided by 3600, 5.36 meters per second squared. And that is the acceleration of a cheetah on average doing that. Okay. All right, so that's that. I think one of you got it right. Oh, actually, quite a few of you got it right. Okay, good. Okay, yeah. Another question. Let's try here. If a train accelerates at minus 5 meters per second square, and it's traveling at 30 meters per second at the moment, how long will it take for the train to stop? Okay, this one is very straightforward. Again, I think, okay, what concept is involved here? Definition of acceleration, probably acceleration or constant acceleration motion. And what are the quantities I know? It is traveling at 30 meters per second, which means my starting velocity is 30 meters per second. I'm also told the A, right? A is negative 5 meters per second squared. And then what am I looking for? I'm looking for T, right? So is there any equation that involves V naught, T, and A? Sure, I know A is equal to V minus V naught over T. So if I can, so what else is missing in this equation? V. And I think about it, okay, what is my final velocity then? Because V is my final velocity, right? What is my final velocity? Since I'm coming to a stop, my final velocity is 0, right? So therefore, my negative 5 is 0 minus 30 divided by T. So my T better be 6. So in 6 seconds, the train's going to stop. Okay. All right, so that's that. So they can throw different kind of questions at you, but the key idea is almost just that, right? Just that equation used in different ways. Now, let's try this one. You are designing an airport for small planes. One kind of airplane that might use this airfield must reach speed before takeoff at least 27.8 meters per second and can accelerate at 2 meters per second square if the runway is 150 meters long, can this airplane reach the required speed for takeoff? Okay, that sounds very complicated, but let's think about what are the things we can use. And at this point, you haven't had these equations memorized, so you can go back and forth and reference them. But during your homework process, I highly recommend you start to try to memorize these equations. Okay, all right. So, well, let's see. I know I'm doing constant acceleration because they told me there's acceleration here. And what are the things I know? I need the VF or V to be 27.8. I know V0 because I'm starting from rest, right? I need to start accelerating before takeoff. So V0 is 0. So this is in meters per second. And I know then the runway is 150 meters long. So in other words, my delta X is 150 meters, right? And I think, okay, to myself, which equation then involves these quantities and the quantity that I am kind of like interested in, which is V here, right? Also, I have A. So which equation involves these kind of things? V naught A and delta X. This one. In particular, this one is very, very useful for one advantage. It does not include time. This is the only important kinematic equation that really doesn't involve time. Everything else is based on time. So if you need something, or if you have an equation, or you have a scenario that you just don't care about time, you're neither given time or you are not solving for time, then chances are you can use this one to your advantage. Okay? So this equation says your V square is equal to V naught square plus 2A and then essentially X minus X0, or in other words, delta X, right? X minus X0 is the same thing as delta X. So let's see. In fact, I actually just want it to be greater than it, right? Because I want a speed that's at least that. So I want to say 27.8 square. Is it less or equal to, that's 0, plus 2A, which is 2 times 150. And that's 600, right? And this one, 27.8 square. Actually, let's not assume that. Let's just say use the equation. V equals that. So if I accelerate for the full 150 meters, what's the speed I'm going to reach, right? I'm just only going to speed. So the speed is equal to that. So V is equal to square root of 600. In math, you would say V equals to plus minus square root of 600, right? But we know that we're gonna discard negative V. It doesn't really matter here. Well, we know it's going forward in the same direction. So that's gonna be like what, 10 root 6? What's 10 root 6? Let me just do 600 and then square root that. And V is equal to 24.5 or 24.5 meters per second. Is it enough? Nope. No, it is not enough for part A, right? Because this is less than the required speed. Then B, if not, what minimum length must the runway have? Okay, so for minimum length, then I would just want my plane to barely reach the 27.8. I'm going to use exactly the same equation because I still don't care about time. So therefore, V square is equal to V naught square plus 2A delta X. I'm solving for delta X here. I know all the other things. I want the speed of that, and that's 0, plus 2 times 2 times delta X. Then delta X is equal to 27.8 squared divided by 4, which will give me, let me calculate that. 27.8 divided by 4, 193 meters is the minimum runway length that I need for this particular airplane to take off. And you can see how kinematics can really help with real life scenarios. Yeah, like these kind of things. Okay. All right. Now, do I have time for that? Let's skip that one. Okay, here's a problem solving strategy. I kind of did that already. Let's take a look at this one. Yeah, let me use this steps to do this one as well. How long does it take a car to cross a 30-meter wide intersection after the light turns green if the car accelerates from rest at a constant 2 meters per second square? Reread. How long does it take? So I'm asking for time. A car to cross a 30-meter wide intersection. So that's like delta x that I need. After light turns green, if the car accelerates, so this is A, right? So I did the reread part. I did the objective. The objective is only for T. Draw a diagram. I don't really need to draw a diagram. I think I know this is 30 meters. This is the intersection, right? So you just need 30 meters to do that. So if you want to draw it, that's fine. In this one, I would say drawing a diagram is not that important. It's simple enough. But for a more complex problem, you should. Known quantities, I did that. Principles in physics, well, constant acceleration kinematics, right? I'm not doing constant velocity, I'm doing constant acceleration. I also know that I start from rest, so V naught is 0 as well. Principles in physics, that's that equation. So several equations to choose from. I have the x equals to x naught plus v naught t plus 1/2 at squared. I have the v equals to v naught plus at, and I have the v squared equals to v naught squared plus 2at, 2a delta x, right? And which one should I use? Well, I'm solving for t. I don't need that one because this one doesn't involve t at all, right? And for this one, do I know the initial? Do I know the final? I don't know the final, right? So I cannot use this one because I'm missing information there. Can I use the first one? Yes, because if I move this over, that's delta x, right? So I can say this is, I want this to be 30, right? And I want, this is 0. I know the initial velocity, which is 0. So that v0 does that. And then 1/2 at squared, I also know that because there's 1/2 times a, they told me it's 2, and then t squared. So the only unknown in here is the one that I need. So perfect. So this is going to be the equation that I will use. Solve and calculate. So 1/2 times 2 is just that. So I got t squared equals to 30. So t equals to square root of 30, whatever that is. Square root of 30 is going to give me 5.5 seconds, essentially, rounded. And solve and calculate, is this a reasonable answer? Yes, it takes about 5 seconds to go to accelerate a car and pass the intersection. A bit on the slower end, I say. But yeah, it's reasonable. Unit check, my time is measured in seconds. Great. Yeah, so that should be a reasonable answer, and I can move on. Okay. All right. And I'm not going to do that. And I think I don't have enough time to completely dive into free fall, but we'll talk about that. So falling objects, as you guys know, the famous story of Newton discovering gravity, apple fall on his head. So let's say we drop an apple, right? And drop an apple. So if we take a multi-flash photograph, which means every single photograph is taken at the same interval, like 0.01 second or something. We keep taking picture, and it looks like the intervals of travel are getting bigger and bigger and bigger and bigger, right? It wasn't falling that fast, but it's falling faster and faster and faster. In other words, the speed of the falling seems to be increasing and seems to be increasing in the linear manner. What does that suggest to us? It suggests to us that a falling object has a constant acceleration. A falling object is accelerating, it's falling faster and faster. That's why if you jump off a table, not gonna hurt too much. You jump off like the second floor, you're probably not gonna hurt that much. But if you jump off the third floor, you're gonna break a leg, right? If you jump on the fourth floor, you're gonna die. So even though it doesn't seem like the height is increasing much, the height is increasing linearly, But if you jump off a building or throw something off, even just a little bit of extra is going to cause the speed to go much and much faster, and therefore having much bigger impact when it lands. That's why falling is such a dangerous thing, because it doesn't follow constant velocity, it follows constant acceleration. And the second one here, if you drop a ball and a light piece of paper, what happens? The piece of paper is going to float in the air and then slowly, very slowly drop down, but the ball will drop down, right? But if you really crumple the paper and then condense it, you squeeze it and then drop it, it will probably not drop as fast as the ball, but it will drop close to it. Okay, which kind of should give you an idea what the beginning question we had at the session today is going to be. And same thing here. If you drop a rock and a feather in air, this is dropping in air. The feather really doesn't drop that fast. The rock goes down. But if you just vacuum it, suck out the air, you drop a feather in the rock, they will drop exactly the same speed. Which means the things that drop slow, like the feather here and the paper here, really has much to do with air resistance. So in an environment where you don't have air, things are going to drop at the same rate. And also things that don't really suffer air resistance much, like rocks, then you're going to drop at the same rate. And it turns out, on the surface of Earth, as long as we're neglecting air resistance, the acceleration due to gravity is a constant 9.8 meters per second square. Okay, and remember, like for the cheetah is only doing like 5 meters per second square, and he is considered the fastest animal on Earth, but gravity is doing 9.8, and that's why falling is so dangerous, because it's almost twice as the most powerful animal, right, when it comes to speed. So that's that. Okay, and this is called we use it a small letter g for gravity, and we consider this to be called the gravitational acceleration, which has a unit meters per second square. So that's the basics for falling object, and falling object is essentially a one-dimensional constant acceleration problem. And for all of the kinematic equations, we can rewrite that. So the kinematic equation, the one that says x is equal to x naught plus v naught t plus 1/2 at squared. Well, we're going to do y because we're falling, right? So let's do y naught x. Y is equal to y naught plus v naught t plus 1/2 g t squared. However, since we define g to be a negative number, we usually do that, right? Because we know gravity is going down, and we usually define the upward direction to be positive. So when the gravity is going down, we write it this way. But that's a minor detail. As long as you plug in the right number, knowing that it's going downward, you're good. Let's try an exercise here. Return to the chapter opening question, page 21, answer again, assuming minimal air resistance. Try to explain why you have answered differently this time. Well, the two rocks, even though one may be 5 times as heavy as the other, I forgot the exact setup, but let's say one is 5 times as heavy, the other one is lighter, they're going to fall exactly at the same rate. Okay, and we're going to dive into like exact details why they've, again, kinematics is the study of how things move, not why things move. That comes from dynamic, which is unit 2. We'll do that later. But for now, just know that if you drop something, as long as air resistance can be ignored, they're going to drop at the same rate. Okay. Let's see here. Oh, that's the problem. Okay, that's I pasted it. Okay. All right, cool. Let's see here. Example problem: falling from a tower. Suppose that the ball is dropped from a tower. How far will it have fallen after t equals to 1 second, 2 seconds, 3 seconds? Ignore air resistance. So this is fairly easy because I'm just caring about distance travel. So I'm going to use this one, right? So delta y is equal to y naught plus v naught t minus 1/2 gt squared, right? They're given g is given we're going down, right? So therefore, this is 0. This is 0. I assume I start from 0. This is 0 too. I assume I don't give it the initial speed. I'm just dropping it. So the initial speed is 0. Tell this out. And so it's just that minus GT squared. If you plug it in, so let's say delta y of 1. So 1 second later, you're going to drop 1/2 times 9.8 times 1 squared. So there's t squared here. You're going to drop 4.9 meters in 1 second. In 2 seconds, you're going to drop 4 times that, which they calculated for you. That's negative 19.6 meters. And in 3 seconds, you're going to drop 44. And you can see that it's really ramping up quite quickly. 4.9 to 19.6 to 44. Yeah. 3 seconds later, you drop like 44 meters a lot. 44 meters is like 12 to 13 stories high. A pretty high building you drop off on. So yeah, if it takes you 3 seconds to fall, you're dead. Okay. Number this one, thrown down from a tower. Suppose the ball is no longer being dropped from the tower. Oh, by the way, this is exactly what Galileo did. Galileo stood on top of the tower Pisa and then dropped, I think, a rock and a wooden ball, and then proved that gravitation is the same for everything, despite the wind. Suppose that the ball in that is thrown downward with initial velocity of 3 meters instead of being dropped. What then would be the position after that? So in this case, I'm still using the same equation. Y is equal to y naught plus v naught t plus rather minus 1/2 dt squared. So y is going to be, that's still 0. This is no longer 0 because now I give it a initial speed. Not only I'm dropping it, I'm literally throwing it down. I really hate that rock. I want to hit. I wanted to hit the ground as hard as I can. So I'm giving it a velocity downward. So that's -3. Yeah, -3 times t minus 1/2 times 9.8 times t squared. Right. So that's y equals to -3t minus 4.9 t squared. Plugging the numbers. 1, that's going to be -3 minus 4.9, so minus 7.9. Y of 2 will be -6 minus whatever we got earlier, right? Because the later part is giving the earlier stuff. So that's going to be negative 25.6, and then meters, and then y of 3 is going to be negative 3 times 3 now, so 9 minus, that's 44.1. So minus 53.1 meters. Again, you can see it ramps up rather quickly. And not only does this ramp up, this also pretty much ramps up quite well. So yeah. So if we compare these answers, like, you know, if you, which make intuitive sense, right? If you're not just dropping it, if you're throwing it down, it's going to travel even further every second. Yeah. Okay. So that one is the opposite. If you throw it upwards, see what happens. I think that's all the time we have. So let's do this one, and then we'll stop here. If a person throws a ball upward with an initial velocity 15, calculate how high it goes. Ignore air resistance. So interesting. So what happens when you throw a ball upwards? It's going to go up, go up, go up, and then it's going to stop and then start falling down, right? That's intuitively what's going to happen. And in the future, you might be asked to draw velocity diagrams, which is say, okay, I have an initial velocity of 15, and then after that, because gravity is accelerating downwards, so my speed of going up is getting smaller and smaller until I hit the stop, and I'm going to fall down faster and faster, right? So that's kind of like a speed diagram. But yeah, how high it goes? Well, so I just care about when it hit the highest point. Quick question. Let's see, Aiden, if you can help me. If I throw a ball up and the ball hits the highest point, what's the ball speed at the highest point?
Is 0.
Yep, exactly. It has to temporarily stop in order for it to start falling down, right? So the speed of the ball, or the velocity of the ball at the very top when it hits the height, is going to be 0. And I started throwing up with 15 meters per second. So this is my V0. This is my V. And then what can I figure out? Well, in the kinematics equation, I have an equation that doesn't involve T, which because here I'm not calculating T and I'm not given T. So let's use that equation. V squared equals to V naught squared plus 2A delta X, or in this case, delta Y, I guess. Plugging numbers. My V is 0. I want the ending velocity 0. My initial velocity is 15 squared. It's positive because I'm throwing upwards. Plus 2A, what's my acceleration? A downward 9.8, right? And then Y, delta Y, and how high it goes. I might as well just label it height, I guess. So yeah, but then I get 15 squared is equal to 19.6 times H. And H is going to be 15 squared divided by 19.6. Oh, by the way, I believe on the AP exam and on most physics exams, you are allowed to approximate G instead of 9.8. You're allowed to do G roughly at just 10 meters per second squared to make your calculation easier. But yeah, but most homeworks and during a school year, you're probably going to be required to use 9.8. So yeah, 15 squared divided by that, 15 times 15 divided by 19.6. I get 11.5 meters. If you throw a ball this fast upwards, it's gonna hit about 11.5 meters above and then start falling down. Okay. All right, cool. Yeah, so that's the illustration of this. How much do I have left? Okay, so there's just some example problems. Okay, cool. Let's stop here for today. I know I covered quite a few topics, but the key thing really is the harder thing that you really might need to review and focus on is the constant A world with these equations. Yeah, everything else is basically just definitions of, what's displacement, what's distance, what's velocity, what's acceleration, that kind of stuff. And then the real calculation really comes from these things. Okay. All right. Let's stop here for today. I will assign the homework later, and I will see you guys on. Was it Thursday? Yeah, I will see you guys on Thursday. Any last minute questions?